This is Chapter 13, Section 2, and it's on the ozone shield. The objectives are to explain how the ozone layer shields Earth from much of the sun's harmful radiation, to explain how chlorofluorocarbons damage the ozone layer, to explain the process by which the ozone hole forms, to describe the damaging effects of ultraviolet radiation, and to explain why the threat to the ozone layer is still continuing today. The ozone shield. So the ozone layer, it's a layer of atmosphere that's roughly 15 to 45 kilometers up in our atmosphere, and it's this little layer where you have these ozone molecules. And an ozone molecule is 3 oxygen atoms, so O3, 3 oxygen atoms bound together, and they absorb the ultraviolet solar radiation. So it kind of acts almost like sunblock to the Earth is how you can think of it. And the reason why we want the ozone layer to absorb the ultraviolet radiation is because UV light is going to be harmful to organisms. Specifically, it damages the genetic material in living cells. So if we could block out some of this UV light, again, it acts like sunscreen. And it's located in the stratosphere, the layer of the atmosphere being the stratosphere, where the ozone layer is at. So there are some chemicals that can cause ozone depletion, and these are called chlorofluorocarbons. And chlorofluorocarbon is basically a chain of carbons, where normally this chain of carbons would have hydrogen atoms bound to it, like that. What happens with these molecules is that some, or mostly all of these hydrogen atoms get replaced by chlorine or fluorine. And these are kind of considered something of miracle molecules. You know, they're very stable and they're really useful as coolants in refrigerators and air conditioners, and also for cleaning solvents. They're used for propellants and spray cans. However, it was discovered that they were starting to destroy that ozone layer in the stratosphere, and so we had to start restricting our use of them. So again, at Earth's surface, these CFCs are stable. They won't combine chemically with anything else. However, once these CFC molecules get into the stratosphere, specifically over in the North and South Pole, these molecules will begin to break apart, and they'll start attacking the ozone molecules that make up the ozone layer. And this is sort of the mechanism of how the CFC molecule breaks down and attacks an ozone molecule. So starting from the left, you have UV light. And this UV light is going to damage or break apart this CFC molecule, releasing a chlorine, or this could also be fluorine, but they're just showing chlorine here. And chlorine will go and react with ozone. And it's going to break down this ozone to form a chlorine monoxide, ClO, and oxygen, molecular oxygen. So coming off here, you have O2 as well. And this chlorine monoxide can then also react with another ozone molecule, doing something of the same thing, except instead you have the replacement of this chlorine molecule and then the release of 2 oxygen molecules. And then this original chlorine molecule can kind of start the process over again, you know, right back here. And what's especially so right here, what's especially so dangerous about this is that just one CFC molecule can destroy up to 100,000 ozone molecules. So pretty powerful stuff. How it was discovered was in 1985. You had a group of scientists working in Antarctica, and they ended up measuring the ozone layer and found that it had thinned by about 50%, from 50 to 98%. And specifically, this is happening during the spring. So levels of the ozone in the ozone layer is going to vary over time, but it specifically is going to decrease the most during the spring, and I'll explain why in a few slides. So once these scientists published their work, some NASA scientists followed up on their research and looked at some data from the Nimbus 7 weather satellite, and they're able to see some definitive signs of that ozone thinning. So basically, the result of all this was some pretty powerful evidence that we need to do something about um, these CFC molecules, so that we don't completely destroy our ozone layer. So you had some groups of governments coming together and working to phase out the production of those CFC molecules and replacing them with some other chemicals that we can use in our products. And the result of this is that the ozone layer is no longer decreasing. And this is some pictures of excuse me, the ozone layer here in blue from 1980 to 1990, and then to 2000, where I believe the hole peaked in size in 2000, and then it's kind of remained somewhat steady, and actually the holes decrease in size going on. So how does this hole actually form? We mentioned the UV light, but there's a couple steps that happen before the UV light. So over in the North and South Pole, it's obviously really, really cold. And what can happen is you have these strong circulating winds called the polar vortex. And this polar vortex is going to separate your cold air from your warm air, creating some super, super cold air. And within this mass of really cold air, you have polar stratospheric clouds that are going to form. And these clouds are going to form right at about 21,000 meters above the Arctic and Antarctic during the winter and early spring. And just to give you an idea of how cold this air is where these clouds form, it's below negative 80 degrees Celsius, which is almost unimaginable, at least for me. And on the surface of these polar stratospheric clouds, you have the breakdown of those CFC molecules. And to remind you of the structure, it's a bunch of carbons, and then your chlorine, maybe some fluorine, some other chlorines, and you have the breakdown of these molecules where you start to break off these halogen molecules to form molecular chlorine or molecular fluorine. And then during the springtime, when you have the return of the sunlight, you have the UV radiation, which is going to break apart your Cl2 and your F2, and it's going to create the individual chlorine and fluorine atoms that will then start to attack the O3 ozone molecules. And this ozone hole is going to last for several months. I mean, it kind of will reform a little bit, but not completely during the fall and winter time. And then a natural question is, okay, if we produce ozone from our combustion engines, like our cars and our factories and stuff, why doesn't that ozone we produce just sort of fill in that hole? And the reason is because ozone is a very chemically reactive molecule. And so the ozone that's produced down where we're at is not going to make it all the way to the stratosphere to fill in that ozone hole. It's going to react and break apart into something else before it gets that far. And again, some of the effects of the ozone, of UV radiation, why we care about the hole is because it's going to damage genetic material. And this is just a diagram showing how the ozone layer works whenever it's there properly, where it's going to kind of absorb and or bounce off some of those UV lights. However, if you have the hole here, then that UV light can pass on through and get to the earth. However, another thing that can happen is that the UV light can kill phytoplankton. And to remind you of the energy pyramid, phytoplankton in your marine ecosystems, they form the very base of this pyramid, where there's a lot of fish and whatnot, marine organisms that are going to eat on these phytoplankton, where if you're reducing and killing off the amount of phytoplankton because you have more UV light, then you're going to be reducing the amount of fish that are going to be produced further up on the food chain. And that's going to decrease the amount of fish that can be caught in fisheries, harm local and global economies, and just can disrupt complete food chains and food webs. And also you're going to have an increase in carbon dioxide because phytoplankton are doing photosynthesis. They're taking that carbon dioxide and they're combining it with sunlight to make and water to make their sugars or make their food. Another thought is that increased UV light can contribute to decline in amphibians, such as toads and salamanders, because the UV radiation can harm the eggs in different life stages of amphibians. And too much UV light can interfere with photosynthesis as well. And this is just a chart summarizing what I've just mentioned. Basically, you don't want too much UV light. It's not a good thing. The Montreal Protocol was a group of nations that met in 1987, and that they kind of spearheaded the effort to limit the production of CFCs. And then back in 2010, the World Meteorological Organization came out with a report, um, showing ozone depletion and reporting that a lot of the ozone depleting substances like your CFCs have been phased out. Um, and even though we've phased out, aren't producing much of any of these CFC molecules, a thing to remember is that they can remain active for 60 to 120 years in the stratosphere. So there's still, even though we're not making them anymore, there's still CFC molecules that are active over in the North and South Pole in the stratosphere. And this is a graph showing, back in 1986 where we were at with CFC production, and then, not even 10, only 8 years later, we got down to virtually zero. Um, so, something of a success story compared to, things like global warming and climate change, where it's hard to get everybody on board with a common plan. Okay, that's going to do it for this section.